Welcome back, class. In this video, we're going to be doing a problem to illustrate how to find the pH of a weak acid. Now, as we've talked about in class, weak acids exist in an equilibrium situation. So we can illustrate the equilibrium equation of a weak acid as follows. We have, in this case, our acetic acid plus water is in equilibrium with the conjugate base of acetic acid and hydronium ion. So the weak acid equilibrium is going to take this form. Now, when we do these problems, you're going to see that no matter what the weak acid is, the equilibrium is going to follow the same format. You're going to have, of course, a different acid and a different conjugate base, but the weak acid equilibrium will always take this sort of format. So our first step in solving this kind of problem is to write out our equilibrium. Now, another piece of information that we'll need is the Ka. Now, either that Ka will be given to us in the problem, or we can look it up in the table in the book. Now, there is a small table in the chapter, but there is also a much larger table in the back of the book in the appendix. So the Ka for acetic acid is 1.8 times 10 to the negative fifth. So based on what we learned in chapter 16 about solving for the concentrations at equilibrium, our technique is to use one of these rice or ice tables, depending on how you word it, where the R is the reaction, or in this case, the materials that we're looking at. So remember that water is not included here because it's not going to be in the equilibrium expression. And so we have our reactant, acetic acid, we have our conjugate base, the acetate ion, and hydronium ion. Now, in this particular problem, we're told that we have a 0.015 molar acetic acid solution. So what that tells me is that at the very beginning, all right, when I first make up this solution, I have a 0.015 molar concentration of acetic acid, and I have essentially 0 of the conjugate base and hydronium ion. Now, these are always written as approximately 0 in the text because, remember, there's always some hydronium present because of the autoionization of water. But in practical sense, there's 0. And let me go back here. We really only need that on the hydronium ion, not on the acetate ion. Okay, so let's go through our process for figuring out our equilibrium expressions via our rice table. So we're going to quote our changes in accordance to a variable. So we have a 1-to-1-to-1 stoichiometry. So we can see that our reactant is going to go down as we approach equilibrium, and it's going to go down by x. Our products are going to go up by x and by x. And so that means our equilibrium can be written as 0.0150 minus x, 0 plus x, or just simply x, and for hydronium, again, simply x. So now we have our expressions. So now we're going to plug this into our Ka expression. So let's remind ourselves that the equilibrium expression for this is going to be the Ka equals our products over reactants raised to our coefficients. So that's going to be the concentration of C2H3O2 minus concentration of hydronium ion over the concentration of our acid here. Now, we can see this equals, right? We can plug in our variable expressions. 1.8 times 10 to the negative fifth equals x times x over 0.015 minus x, and that's going to be our position that we're going to solve for x. Now, one thing that we're going to keep in mind on most of these acid and base equilibriums is that we can go ahead and use our x is small approximation here, because these are very typically very reactant-favored equilibriums, right? Remember, weak acids don't make very much hydronium ion, and so their Kas are usually quite small, and assuming we have reasonable concentrations, right, we're typically at least 3 orders of magnitude apart. So almost all of these we can make the assumption without any problem, and this will simplify the math. Now, of course, a lot of these you could solve using a quadratic, and there's nothing wrong with doing that. But to save us some time, we're going to make this approximation, and we can always check it. So remember, when we make that approximation, we just assume that any addition or subtraction of x is 0. And so now our expression simply becomes our Ka value equals x squared over 0.0150. Now it's pretty straightforward to solve our math here. We can bring up over our concentration, and we get 2.7 times 10 to the negative 7 equals x squared, and therefore take the square root, and x equals 5.2 times 10 to the negative 4th for x. So now we have our x value. Now, remember, that's just half the story, right? We have to plug our x back in to our equilibrium expressions so that we can get our equilibrium concentrations. So for our acid, it's going to equal 0.0150 minus 5.2 times 10 to the minus 4. And so this is going to equal 0.0145. Then for our conjugate base, or acetate ion, it's simply going to equal x. And so the concentration is going to equal 5.2 times 10 to the negative 4. And our concentration of hydronium is again going to equal 5.2 times 10 to the negative 4. These, of course, all molarities. Now, we want to check to see if the approximation was okay. So we're going to, again, look to see if our x value (5.2 times 10 to the negative 4 divided by our initial concentration, 0.0150 times 100, is that going to be equal to less than 5%? And what we get is it's right around 3.46%, so we can say it is valid. So it was perfectly fine to make the approximation, so we're okay with our concentration. We got one. Now, anytime we're doing these kinds of problems, what we have to understand is, unlike sort of our normal equilibrium problems, where we're kind of interested in everything, really all we're interested in here is the hydronium ion concentration, because that's what's going to allow us to calculate the pH. So we have our hydronium ion concentration, and remember that the pH is equal to the negative log of our hydronium, which in this case equals the negative log of 5.2 times 10 to the negative 4. So if we solve for that, we get a pH of 3.28 for this problem. So one of the things that we'll get used to when we do this is that when problems are asking for the pH, what that is another way of saying is find the hydronium concentration at equilibrium and use that to find the pH. Or understanding that when they give you the pH in a problem, really what they're giving you is the equilibrium hydronium concentration. And that's oftentimes what we need to use. So we want to get used to that sort of thought process. All right, so this is one problem. Now we're going to do a few more problems here to get used to working with these acid-base equilibria.